Okay, now that we have assessed the performance and overall efficiency of these two systems from a qualitative standpoint, using that visual model, I wanted to also give you a comparison between these two systems from a mathematical perspective so that you can really get a grasp of how much more efficient the braced frame system is when providing stiffness from a lateral perspective compared to the moment frame. So of course, whenever we're talking about efficiency and we're trying to compare two different systems, we first have to start with how much material are we using. Of course, the amount of material used doesn't always provide a complete picture of the cost of a system, because we're not taking into consideration the smaller details like connections. And as I've mentioned before, the cost of a fixed connection is significantly more than the cost of a pinned connection. However, for the sake of this discussion, we are only going to be looking at the amount of material used. So let's start with the amount of steel used in this moment frame. As you can see, I've provided the calculation already. And it was really a fairly simple calculation because all of the numbers are already provided here. You can see all it took was multiplying the weight of the beam times its length and adding the weight of both columns times their length, and I got 4,475 pounds, which is equal to 2.2 tons, roughly. Now let's do that same calculation for the braced frame. So again, we have the same beam weighing 35 pounds per linear foot. It is 25 feet long, so that gives us the weight of the beam in pounds. We now have two slightly smaller columns with this braced frame system here. They are each 65 pounds per linear foot and 20 feet tall. And again, as we discussed earlier, the reason why the moment frame columns are larger than the braced frame columns is because the moment frame is relying on the stiffness of these columns, whereas the braced frame system does not rely on them whatsoever for lateral stability. Instead, they are sized purely for carrying the gravity loads. Now, of course, with the braced frame, we have one more element here, that is the brace itself. And in order to get the weight of this brace, we first need to calculate its length. And of course, we can do that using Pythagorean theorem. So now we just need the weight of this brace in pounds per foot. And unfortunately, that's not part of the tag. So we need to go to our shape database, look in the weight column for an HSS 6x6x3/8, and find that it is 27.48 pounds per linear foot. And so we get a weight of approximately 4,354 pounds for our braced frame system, which, converting to tons, we simply divide by 2,000, and we get roughly 2.2 tons again. So these two systems have very similar weights, meaning that they have very similar amount of material used, meaning that they will be roughly similar in cost, neglecting, of course, the additional cost of connections. So we're starting from a very similar base point here. We've used the same amount of material. And now let's compare how much stiffness that each of these systems provides. So in order to do that, we are going to need to introduce two new stiffness formulas, one for the moment frame and one for the braced frame. And these two new formulas may look frightening at first, but they actually might be more familiar to you than you think. So let's first define what we actually mean by lateral stiffness. Mathematically, lateral stiffness is a quantitative measurement of how much force it takes to move a structure horizontally by 1 inch. In other words, these two formulae give a value expressed in units of kips per inch of lateral movement. kips per inch. The higher the value, the higher the stiffness. In other words, the more force it takes to move that structure that 1 inch. So again, both of these formulas will provide a value expressed in kips per 1 inch. Kips per 1 inch. So this hopefully should sound a little bit similar to another more familiar set of formula used in structural analysis. That is our deflection equations. In structural analysis, we use deflection equations to come up with how many inches a structural element deforms given an amount of force in kips. So we're playing with the same units here, but working in a different direction. In deflection equations, we're given a force in kips, and we solve for the amount of deflection in inches. In stiffness equations, we're given a deflection of 1 unit inch, and we solve for the amount of force it takes to get there. So now let's look a little bit closer at these formulas with this new information in mind. And let's start with the moment frame stiffness equation. Recall from our mola model example earlier how the columns appeared to sway and deform in this shape that I've replicated here. And let's consider the look of that shape for just a moment. Of course, up at the top, the column was restrained by that fixed joint at 90 degrees. However, at the base, it was not restrained against rotation, and so it deformed in this manner, giving us this shape. Now let's imagine that shape rotated 90 degrees, counterclockwise. And let's draw that shape. So again, this is at 90 degrees, and then it slowly deflects downward like this. So, does this shape look familiar to you? Well, if you've studied your beam deflection equations, then yes, it should. Because it just so happens that this is the exact shape of a cantilever beam with a point load at the end. So there is a mathematical equivalence here between a moment frame column and the way that it deflects or distorts, and a cantilever beam with a point load at the free end and the way that it deflects and distorts. And I'll prove that to you by bringing you back to these beam equations. And if we take a look at the deflection equation at the free end, you can see we have this PL cubed over 3EI. So that is the deflection equation for a cantilever beam with a concentrated load at the free end. Now let's compare this formula to our stiffness formula. As you can see, all the same variables are here with the exception of the force, because of course the force is what we're solving for with our stiffness equation. But you can see this 3EI is there, but now in the numerator, of course, because as I mentioned before, the stiffness equations are the inverse of the deflection equations. And this L cubed, instead of being the length of a beam, is the length of our column, cubed. And of course, because we have two columns, we multiply by 2. And that provides us with the stiffness of our moment frame. This, to me, is honestly the real beauty of mathematics. Mathematics does not give regard to individual reference planes. In other words, math still works the exact same way whether you're viewing it standing straight up, lying on your side, or even hanging upside down. It's all the same math. Alright, now let's look at the stiffness equation for a braced frame. And again, let's ask, does this look familiar at all? Well, I've already kind of spoiled it for you by leaving that formula there, But recall that when we pull on a member in tension, we can measure the amount that it lengthens, the change in length, with this equation that we derived earlier, PL over AE. In other words, it's the force applied times the original length of that member divided by its cross-sectional area and multiplied by the modulus of elasticity. PL over AE. As you can see, in the stiffness equation, once again, we have all the same variables flipped upside down. However, we do have one new additional variable here, and that is our cosine squared theta. So where does this come from? Well, of course, with our original equation, our force P was aligned with our member. But of course, when we look back up at our braced frame here, the force that is applied is not aligned with the member. And so there needs to be some trigonometry that occurs in order to get that force into the brace. And that is where the cosine squared theta comes from. But otherwise, this is the exact same formula that we've seen before, just flipped upside down. So these are the two formulae for stiffness, and I'm showing these to you for one main reason. I want you to pay particularly close attention to the denominators in both these equations. Notice how the length term in the moment frame equation has a cube, while the braced frame does not. Now there's this sort of trick in mathematics whenever you look at a formula to first look at any variables that are squared, cubed, etc. Because of course squaring and cubing numbers, putting them to a power, in other words, makes those numbers, once you plug them in, become very, very large very, very quickly. So if you want to get an idea of the rough order of magnitude of what kind of value you're going to get out of an equation, you first look for the powers. So what happens when you cube a number? Well, as I just said, it gets very large very, very quickly. And what happens when you have a very, very large number in your denominator of your equation? Well, your final value gets very, very small. So here, with the stiffness of our moment frame, we can tell already that we're likely going to get a pretty small number here, compared to with the braced frame, where we're not cubing that length in the denominator, we're likely going to get a much larger value. So again, here in the mathematics, we see how the moment frame provides significantly less stiffness compared to the braced frame. So now let's go ahead and plug in some numbers and prove that that is true. So our variables here are, for the modulus of elasticity of steel, it's 29,000 kips per square inch. Our moment of inertia here for these columns, assuming that they are oriented in their strong axis dimension here. In other words, if we were to look at this frame in plan view, what we would see is the columns oriented in this direction, so that they take bending in their strong axis, rather than orienting them this way, such that they have bending in the weak axis direction. A moment frame with columns oriented in this direction is really not going to provide much stiffness at all, because it's bending the column in the weak direction. So ideally, we always want to keep columns in moment frames oriented this way, so we're at least taking advantage of that strong axis bending. So anyway, back to here. Our moment of inertia for a W14 by 90 column, we can look that up. 14 by 90, moment of inertia in the strong axis or X direction, 999 inches to the fourth. And lastly, the length of our column, we have 20 feet. And of course, because everything else is in inches here, we're going to want to convert that 2 inches. Now we can plug everything in. Of course, don't forget to cube the value down here. And we get approximately 12.6 kips per inch. In other words, it would take 12.6 kips of force in order to displace this moment frame by 1 inch. Now let's take a look at the braced frame. Here our variables are different, of course, with the exception of our modulus of elasticity, again, 29,000 kips per square inch. Here we're taking the area of that brace. So going back to our HSS 6x6 by 3/8. And the area of that is 7.58 inches squared. The cross-sectional area. So again, that's looking at the HSS, or hollow structural section, in cross-section, and taking a look at that area. The length of the brace, as we said earlier, is 32 feet. And again, we will convert that to inches so that our units are consistent. So that's 384 inches. And lastly, we have our cosine theta squared term. So what angle are we talking about specifically here in this formula? Well, it's this angle here that we're looking to plug in. And recall that this is 25 feet and this height is 20 feet. And we also solved for the length here of this brace, roughly 32 feet. Now we have a couple options here of how we want to solve for this cosine theta squared term. We could either solve for theta by first using the inverse of one of our trigonometry equations. For example, we could take the inverse tan equation. Tangent is, of course, equal to opposite over adjacent, so we could take the inverse tangent of 20 over 25. That would solve for theta, and we could then plug that into our cosine theta equation. But we can actually get to a value much quicker than that if we understand what these trigonometry equations represent. Again, recall that cosine theta represents or is equal to the adjacent side over the hypotenuse. We already have those two values, so we don't even really need to solve for theta here. We can just say that cosine squared theta is equal to, again, the adjacent side, 25, over the hypotenuse, 32, that value squared. And so we get 0.61. If you would like to, you could solve for theta and plug it in if you want, and you should get this same exact value. Alright, now let's plug in all of our variables. So 7.58 inches squared. And we get about 349 kips per inch. In other words, it would take 349 kips of force to move this braced frame to the right by 1 inch. That is, of course, a huge difference compared to the 12.6 kips per inch stiffness that we got from the moment frame. So again, mathematically, we now see that braced frames are significantly stiffer than moment frames. They're really not even close. When you take the same amount of area, the same material used, and compare the brace frame to the moment frame, you get so much more stiffness from the braced frame. Alright, so that wraps up the discussion on moment frames and brace frames. I'll see you next time.